Alright, everybody, how we doing today? Doing good? Glad to see everyone here. So, how was those computer assignments first off? Not that bad? Really not that hard, alright? I really went through everything. Yes, what's up?
How about E361? Will there be computer assignments or no?
It just depends. I don't know. For Dr. Morris, I had no say. But Dr. Stewart, I think he does assignments. If you're taking Dr. Stewart's 361, he does assignments. But Dr. Morris, I have completely no idea. So, but if there was a 361D, then of course I would take it. But anyways, yeah, you're out of luck there. But if you fail that class, then you just pass as best as you can. Okay, but this class is I can give my 2 cents. Honestly, I really like the way that Dr. Morris teaches. I've never experienced a group of like engaging students. Like you guys are like sweating. I'll give you guys that. You guys are doing great. Okay, Dr. State, he's doing good too. But he's like a theory guy, and there's nothing wrong with that. But I'll fall asleep too. It's okay. He's like, you know. He's just visiting. He's in 361. How's 361? Stochastic systems?
Yeah.
Learning about PDEs, CDFs, PDFs?
We haven't gotten that far yet.
You'll be there. Pain. Anyways, quantization, all those funny words. Anyways, but other than that, you guys are doing okay. I haven't looked at any of the quizzes. How are those going? He's making you do quizzes every day or something like that?
Yes.
Huh? He doesn't grade them? What about his grader?
What? Oh, wait, how much one?
Yeah, Dewana.
She's not grading mine.
Oh, she's not grading the quizzes?
Where is she? Like, she's not even grading.
Oh, yeah, she's not here. She's got some things going on, so got to give her some slack on that. Okay, yes, what's up? Oh, he's busy. I'm busy too. Everyone's busy. It's crunch time, and I want to make sure you guys get out of here, okay? So, any other questions before we start for today? So,
Would you take the E361 with, assuming
they're both great. I really like both of them.
or E370?
Wait, 370? No, you have to take 361.
You have to take it before 370.
Oh, no, you don't need it as a prereq. You have to take 370 real. 360 goes over frequency responses, right? Or not frequency responses. Z transforms, Laplace transforms, kicking boxes, discrete time, and all these big things. Okay, you guys are doing a lot. You guys seen the magic of the Laplace transform, the Z transform, right? Well, for controls, you go deeper into the Laplace transform and look at stability. Okay, 361 dives a little deeper into the frequency response and stochastic systems. So, what if your system does something random? So. Stuff like that. I'm not so sure, but you'll figure that out. Okay. Anyways, I want to talk about a few problems. Let's just start with this. Everyone can do the following, right? Right. Laplace transform, nothing too hard. Okay. What's his name? If I were to draw, well, this is the zero line, and I don't know. This is 1, and this is -1. It's -2, 1. Stuff like that, right? You guys see that? Not that hard? Okay, I'm going to trick you guys. Or hopefully not. I really hope. This should be trivial by now. If I were to do the following, if I gave you a system like that, right? Is this a stable system? If I were to tell you it's a stable system, what do you got to do? Draw this line right here, right? And draw that region of convergence, right? Stable system, stable pole. What's his name? It not convolves. What's that word? Converges? Or no, not converge. What's that word? Causal. Too many C words. Anyways, everyone understanding what's going on? What if I do the following? If I put a 0 right there, is it stable? Yeah, it's stable. It's just a 0. Okay, so zeros are pretty fun. You'll learn this more in 480 about why zeros are very dangerous because they can either break or make like the best billion-dollar op amp. It's really, really cool. But anyways, if I were to do the following, I'm just going to put a pole right here. Is this a stable system?
Well, it's stable, not causal.
It can be stable if you make it non-causal, right? It's between this area, right? But if I were to tell you tell me if this is a stable and causal system. It's not. It can't be because if I were to do the following, if I were to draw this line right here, the only way for it to be stable is if our region convergence was in this middle right here, right? Between these two poles, right? Then it would include this imaginary axis. But if I were to say, is it causal, as in can I run it in MATLAB, just run it forward in time? It can't, because it's going the other way. It's not, the region of convergence does not include that imaginary axis. All right? Does that make sense? Now I have a better question. How do I get the pole zero plot from this? How do I do that?
Just label each.
So where's my pole?
Your poles are on the denominator.
Denominator. So this is going to be, this is a -1, right? This is where we're going to break our things. So if I were to do the following, S, what do you call it, +1? Makes sense, right? Because if I put -1 there, it's a pole. Easy. Everyone's going to get this, right, on the exam. Okay? The study guide says yes. What about this pole right here? Oh, this is +2, sorry. There you go. Oh, wait. S -2. I don't like it when I see bad work. S +1, S -2. Make sense? Everyone understanding how to build these systems? What about the 0? S -1, right? Is that cool with everybody? All right, now the next question is determine a difference equation for, not difference equation, differential equation from this. Can everyone do that?
Yes.
Yes? Want me to go over it?
If we read, I'm taking partial, then after that going to the exponents, and then the exponents.
Yeah, why don't we just go over it?
And that's it.
So no, I was just going to make you guys do like this. Well, you know this H of S, HS is equal to YS over XS, right? And then if I were to move these poles on one side and the other, so you're going to get the following YS. Should I skip steps? Nah. S +1, S -2, right? Does that make sense with everybody? And then equal to X of S, S -1. All right, are you guys seeing the difference equation coming out right now? Right, and then how do I turn this from this to the, well, first off, I have to multiply these things. So YS, S squared, let me see, this is S, and then, no, I'm gonna write this down, plus S minus 2S, right? Okay, I don't want to skip steps, okay? And then 1 times -2. Everything making sense? Cool? And then, well, let's just simplify things. Okay, I'm just writing this down because I want to make sure I don't lose anyone. S -2, X of S, S -1. And then how do we go back to our real signal? Well, if you see this S squared, right, that means it's going to be a second derivative. So if I were to, let's just cheat, right? Y double prime minus Y prime minus 2Y, right, is equal to X prime minus X. Now you have something to put in MATLAB. Ain't that cool? Or you can put it in that, what do you call it? Remember that computer assignment 5? You can run this and prove your work. Or actually, everything can be proved. I'm going to show everyone on the big camera. You can prove all your problems with the Shams book. Is he making you guys use the Shams book?
No, yeah.
What, really?
No, not yet.
Next week.
Next week?
Next week. After.
Dang, you guys are, yeah, it's okay. Yeah. Yeah, I love this book. This book is great, and I'm probably going to go over problems. But yeah, there's the thing about that Sham. If you guys really, really want a great study guide, this thing gives you hundreds, thousands of problems, and their walkthrough solutions. And I'll probably go over one too. Okay. But anyways, I want to go to okay, no BS. All right. I want to make sure you guys make money and get out of here and have some fun. All right. Everyone can do this. Everyone can look at this pole zero diagram. Right. It was scary back in the day, right? But now you guys are masters, huh? Well, you'll show me that tomorrow after you pass, and you'll get that grade, okay? Everyone can look at this, get this right here, right? And then get to this part. Does that make sense with everybody? And then I'm gonna give you. He's gonna give you a wild, random question. It's very trivial, and if you guys fail me on this, I'll be crazy. Find the step response of the system. And what are you guys gonna do? You're not gonna use this. If you use this, well, you can. Go ahead, be my guest. It's more work for you. You already have the transform. All you gotta do is just multiply this by your not impulse response, your step response. What's the step response of a unit step? U of t to u of s or something like that, right? What's that equal to? Right? Everyone gonna memorize this? Any questions about that?
You're saying just multiply your h of s by
Yeah, okay.
I see what you're saying.
And that's your answer. And someone's going to be chuckling tomorrow saying, I didn't come to class and he told me about it. I'm like, I should have came. Okay, if you don't memorize this, and you can do this, and it's funny because he gives you a lot of information, which you got to know what you're trying to do. But I feel like a few of you are going to use this equation and try to put the step response in there, and you can. It's not that hard. Well, it's a lot of work. Laplace transform is your friend, okay? And if you don't believe me, use MATLAB. Prove it. We did that last class.
You're saying x of s would be the step.
Yep, that's your step response. So I want everyone to go home happy. Okay. I want you going home happy. Okay. I'm gonna write this response again, and I should have used different colors. I'm gonna use this pink. H of s, which was, I'm just going to say it, s minus 1, s plus 1, s minus 2, correct? And this was h of s, right? And then I have this step response, right? Or not step response, just x of s, right? Okay? And then I'm going to do the following because I don't want to lose anybody here, okay? It's convolution in the time domain, but what is it in the Laplace domain? It's multiplication, right? Greatest tool in the world. You can do LT-SPICE, you can do MATLAB, etc. So I want everyone to figure it out for me, okay? So what if it gives you, like, what's his name? A unit step, right? Unit step, U of t, right? What are you guys going to think? Step response, 1 over s, right? What if he gives you the following, which is, I don't know, some amplitude e to the, I don't know, pole t, right? Minus pole, because it's stable, correct? What are you guys going to do? Or s minus pole? No, s plus pole? Right? You're going to multiply this to that. Any questions? And better yet, if the pole is 0, right? If p is equal to 0, right? So that means this exponential doesn't grow or decay, right? What does this p turn into? 0, right? So it's a over s. Trivial, huh? So if you don't memorize anything, if you want to memorize one thing in the world, just memorize this. Okay, please do that for me. Just memorize this. What's this a? What's this a right here?
Some constant?
No, or not just that.
Real part or residue?
Residue. What's this p? Pole. Residues and poles. And then there's a thing called gain, but I don't think he's that crazy or, crazy to give you a gain in a pole or something like that. But anyways, easy A. All right? Everyone's going to do great, okay? I've seen your guys' works. You guys are doing great, okay? Well, from what Joanna's been telling me. So, you guys...
Just like exaggerating a little bit.
Just make me proud, okay? Anyways, what if... I'm going to give you guys another trick question. But the point is, the trick question was, and please, if you start complaining to me, or complain to him, I told you so. Don't forget this, okay? Easy stuff. Stuff right there. You can do this here. And weirdly enough, if he asks on the exam, do not use this, then I guess he really is picky, okay? But anyways, everyone can go from Laplace to time to Laplace, okay? Any questions about that? So what if he did the following? see if I like this. Okay, I think I like this right here. Suppose he did this for you. Need more colors. Life can use more color. There we go, blue and black. Oh no, that one's, it's okay. Does this work? Yeah, okay, I like that. Okay, what if he gives you something like this? I'm just gonna draw stuff. I'm gonna draw a pole right here, right? And let me know. You know what? I'm gonna trick you right here. 0 right there. You know what? I'm gonna put a pole right there just to be angry with you. Okay. Not that bad, right? Pretty chill system. Okay. But then what if I do the following? Let me see. Let me think. Guys, I'm trying to show you what I'm trying to do. Guys, this is in the bottom. Let's go to the top. I'll see what I want to try and do, okay? Let's see if I do the following. Let me just do another circle here, and then let me just do a circle here, a pole there. Okay. So you have these poles, and I'm going to put this as -1, 0, 1, -1, 0, 1, right? What's the systems? How do you get the transfer, not transfer function, just the Laplace transform of this? So we have two poles right here, right? So if I were to draw my numerator and denominators, right? So I have a pole at S, right? And then I have this S plus 1 term right there, right? And then I have the 0 term right there, right? S minus 1, right? Everyone's going to memorize this? Right? Yes? Good. Okay, I hope I'm not wasting my time here. How about this one? I have a pole, right? It's easier to write the poles first because I like poles. So we have a pole at S, right? Cool. And now how about our zeros? Well, we have S plus 1 from this guy and S minus 1 from this guy, right? All right? Everyone getting this? This is page 2. Who's recording me on my their Meta glasses? It's okay. Go ahead, I don't mind. I got mine too. It's right here. I'm playing. They're not here. Nah, they're a little big. But anyways, let's get to the grand scheme of things, okay?
Will there ever be a change for E361 discussion?
Solve the transfer function of, if I give you an output and an input. Can everyone do that for me? So, okay, let's just redefine things, okay? X of S, right? What did we say? It was S minus 1 over S plus 1, right? Remember that, right? Then y of S is equal to S plus 1, S minus 1. And this is where I'm starting to like wonder if I did this correctly, okay? What are we going to do? Divide, right? All right, please. I'm really being nice with you guys, okay? Divide, right? We're going to get these poles and we're going to divide. So don't worry if you're confused like me. Write them down like this, okay? You're going to do this on the exam, okay? Memorize this. Okay? Just think of it like this, okay? Then I'm going to write my y of S, S plus 1, S minus 1 over S, okay? Grab my other marker. We're going to do this part right now, okay? I'm going to use this pink marker or purple marker. Lavender. So this is our numerator term, right? And this is going to go down right here. S minus 1, right? And now this denominator is now on the numerator, correct? So S plus 1. Any questions about that? So now, cancel stuff. What do we see? See this right here and that right there, right? Cancels, right? How about, I don't have another marker, it's okay. How about this guy right here? This guy right there. They cancel out too, right? So let's see if I did this correctly. I don't think I did, but it's okay. I'm just trying to show you an example. You got s plus 1 squared, and that's pretty much it. And that's a pretty ugly system, not going to lie. And then, okay, so let me think about this because I want to reverse engineer what I'm trying to show you. So this guy cancels whatever's up here. This guy cancels whatever is right here. So if I were to give you a real problem, because I want to make it stable, I think. Okay, let's think before I conclude with what I'm trying to say. Did everybody see that? Okay, actually, let me just write this. What's the pole zero diagram of this? It's a double pole,
Double pole, I think.
or not double pole, double zero
Oh,
at 1,
negative 1, right?
or negative 1.
Negative 1. It's S
Okay,
plus 1.
minus 1, and then there's a squared term right there, right?
Yeah.
Is that cool? Not that bad. So let's reverse engineer what I just did. Okay. So I'm saying to you, I have an output system right here, and I have an input system. I have 0 pole 0. I have pole 0, right? But for some reason, I got 2 zeros, and everything else has happened. You see how I have a pole right here, and I have a pole right here, right? What happens if I do output over input, pole over pole? They just disappear. So boom, boom, done. 0 divided by a 0, boom, it's gone. So, but if I have two opposite things, right? My output has a 0, right? And then that means my pole, or my input has this pole. This pole turns into a 0, double 0. All right? Which means I made a pretty crappy problem. So you want to know how I would have designed this? I should have flipped this around. Then I would have had, what's his name? 1 over s plus 1. That would have been an easier one. And then we would have done partial fraction expansion, right? Not that hard. Actually, you know what? I'll do that next, okay? Anyways. Yes, what's up?
So, will you also be going over, like, for example, like eigenfunctions for like the Z transform and the loss? Or that's
Say that again?
you know, like problems where we don't have a simple transform with a unit step, but rather eigenfunctions.
Eigenfunctions, so like magnitude and phase responses, like you just throw a frequency and boom, you get the magnitude and the phase of a system.
No, like for example, say you have some some function as the input, and the output would be h of s or h of z times that input.
Yeah, so magnitude and phase.
Yeah.
Yeah, you might have to see that too. Anyways, you guys know RC circuits, right?
Yeah.
If I put a sine wave into it, what am I going to get? A sine wave out with a magnitude and phase? That's basically what you're saying. But basically, if you knew this, h of s, right, and you had a system, I don't know, 1 over s plus 1 over, no, s, yeah, RC or something like that. I'm just going to guess, okay? Does that make sense? And then all you do is, well, you already know your frequency, right? If I keep kicking things into this box, you can get, that magnitude thing. So if I wanted to, the output in terms of, output, where y of t is equal to, I know what you're talking about, h of s evaluated at some input, right? S is s naught or something like that, some frequency. The magnitude, and then there's an input e, and then let me see, I'm not remembering it. There's a phase here or something like that, but that's what you mean, right? Yeah, that's gonna be, I don't know if that's gonna be on the exam, but it's good to know. Okay. Yeah, basically sine wave in, sine wave out, but it's got a magnitude and phase response. Anyways, back to our normal programming, because I want to make sure you guys get out of here on time. How do we do partial fraction expansion? Well, first off, I can't really do much with this, right? It's double pole, right? So what do you guys know about double poles?
Oh, yeah, so A, it will be A over S plus 1 squared plus B S plus 1. Right?
Yeah, S plus 1 squared plus B S plus 1.
Plus 1, yeah.
Right? Everyone can get that and do the Heaviside equation or Heaviside function or what is that? Is that what it's called? Heaviside or? Yeah, the cover-up equation, okay? It may be on the exam. Wink. What's the other condition? It was like, well, that's this one might be the harder one, okay? So if you see the following, okay? Double pole right there, you gotta think this, okay? Someone's gonna forget this. Actually, you won't forget this. A lot of people won't forget this. People forget this one, okay? When you see this guy right here, don't forget that term, okay? Because if you forget it, then values start becoming off. All right. Any questions about that? What's the other case? Was it because what's that one case where I wanted to do it's like ax plus b. What? Yes.
Irreducible factors.
Irreducible factors.
Yeah.
It's what you're doing, but if you're not doing Heaviside cover.
Oh, that's.
So like if you're trying to do full partial fraction expansion.
Yeah, the painful part, right? Anyways, or actually not. Is it AS? No, it's not AS. It's S.
AS.
Yeah, so this is painful. Okay, I don't think he's gonna do that to you. Okay, let me see. Yeah, he won't. He won't. Memorize this. Okay. Oh, he won't. He may. I don't know. May not. Any questions about this? Okay. Yes. I'll go with you. Yeah, technically it kind of is. It's not that hard, but you need to solve for the A's and the B's. Actually, you're not wrong because we can get this, and then we can get our what's his name? The time not the time domain, the time representation. Yeah. The difference equations or your H of t, right? Because the whole point of doing partial fraction expansion, okay, page 4 is. You're an engineer, okay? And I give you a plant or I give you some control or some type of system, okay? And it's going to have, I don't know, pole, maybe double pole here and some 0 and 0, 0, 0 right there, right? H of S, right? And it's a pretty complex system, right? I want you to tell me how to go from this to, I don't know, what's it called? A e to the minus pt, or you know what, pt, p1t plus b e minus p2 t, and then plus b e to the minus p2 complex conjugate t, stuff like that, okay? Can you do this stuff for me? He basically, can we run this in MATLAB? If you can run, because you can run this in MATLAB, but you want to do this by hand, okay? This is easier to run in MATLAB than this, because this actually costs money. I'll tell you that. AI data machines or something like that, because it's really cool. Have you played with? Everyone's here played with the what do you call it? The Laplace transform toolbox. Not that hard. It was really cool to see all these systems run. You can create massive systems, right? But for your exam, can you get this? Not that hard. Anyways, questions? What about if I did the following? And he might do this on the exam. I'm just telling you. That's a bad circle. If I were to do the following. Can you see that? Hopefully you can. Is this a stable system? Well, all the systems I wanted I want them all to be causal, okay? So is it causal and stable? No, it's not. Or yes, it is. Sorry. Because if I were to draw this donut right here, right? It goes out, right? And it includes that unit circle, right? Any questions about that? What about this pole right here? It's also stable, right? It's all chill, okay? We can draw poles here. If I draw a pole over there, it can be stable if we go non-causal. okay? But I think all the problems he gives you are gonna be causal. He may throw a curveball where just define the system, okay? Do you guys know your pole zero diagrams for Laplace transforms and Z transforms, okay? Any questions about that? All good? Yes, what's up?
When you say define the system, like, not like linearity, or like, he just wants to know causal and stable?
No, there's going to be linearity. Well, technically, all these systems should be linear. If it's an LTI system, what does LTI stand for?
Linear time invariant.
There you go. That means you can do. Come on, convolution.
Yeah.
You remember. Which means if you can do convolution, you can do multiplication in the Laplace transform or Z transform. Any questions about that? Simple stuff. Snap, snap. Cool. Anyway, so which means these systems should, like all these Laplace transforms and Z transforms, they're all linear and time invariant. Okay? So I don't want to talk about those anyways, because you already studied that from, I think, week 2, week 3. The properties of systems, right?
Is that going to be on the test?
I don't think they should, because it's just Laplace transforms.
Okay.
Okay? And Z transforms, okay?
I mean, I just don't, well, I mean, I get how, but I don't justify my answer on like why it's linear, why it's causal sometimes, or why it's stable or unstable. I mean, right in that, let's say, hey, it's like right beside, blah, 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 blah.
They're gonna be linear. Are you not feeling confident about getting a Laplace transform that's not linear? Because it's not.
Like defining the terms, like,
What?
but I don't think that'll be on the test.
No, it won't. It's all linear time invariant systems. You're not going to deal with if you can't do it linearly. You'll see it when you do the Laplace transform because it's not possible. It's a little hard. It's a deeper study. That's way above this class. Anyways, everyone can do something like this, right? And if I were to put a 0 right here, right? Actually, here's a good question. If I have a pole right here and I put a 0 there, what happens to that point in time? It's canceled. Great. You see? Anyways, can everyone here do pole 0 cancellations? Okay, he's going to make you do pole 0 cancellations just like what I did right here. Okay? And then everyone's going to make me proud when he does the following, right? Right? We're going to do this, okay? And basically, what if he gives you x? Okay, you solve for h, right? You solve for h of s, right? You do all your partial fraction expansions, and he gives you x, and he gives you just a pole 0 map. What are you going to do? You're going to do the following. Just multiply things. You guys like how trivial this, or I don't know. For me, it's trivial, but for you, I'm not so sure. That's why I'm trying to ask questions. Like, yes.
Pole 0 cancellation is keep, multiply, flip.
Just pole 0 cancellation.
Say that you have a pole and 0 at the same spot, put the numerator in the denominator, and you cancel out.
Thank you.
So if I have s minus 1 on top and s minus 1 on bottom, those will cancel out.
Yeah. 4. I don't want to waste time on this, okay? Because we got a lot more things to go over because I'm already running out of time. And I don't think I'm going to get to all of the problems that I wanted to. Anyways, okay. This is good for you guys, okay? System 1. Okay, system 1. He's going to give you pole right here and pole right there. But guess what I'm going to do? Right? Easy stuff, right? Not that hard. Okay. System 2. You know what? I'm going to make it even tougher. Right there. I'm just going to put a... actually, it won't be clean. Just keep that there, okay? System 2, right? 0 and 0. And then you know what? I'm going to do this. Just make it a little harder. All right. Oh, yeah. It's at 0.5 minus 0.5. plus 0.5 and 0 DC, right? Or not DC, it's just 0. It doesn't exist at that point. Anyways, and then this right here is 0.5. This right here is minus 0.5, right? Everyone seeing that? And this right here is at minus 0.5, right? Cool. So now I'm telling you, dude, to do the following. Multiply them, right? This is 3, right? What's the result? I should have made more room. This pole right here and this 0 right here, right? You see this right here and you see this right here? What happens? Cancel out, okay? Make sense? How about this right here and this right here? Cancel out, right? But then I introduced 2 new poles and I got a pole right there, right? What's our final plot? Boom. Easy. Pole 0 cancellation. Any questions about that? Because this is very important too. You'll see this a lot in DSP, okay? And this is how you can create a stable system, or make a non-stable system or a causal system or a non-causal system. You can make them causal using like a, you'll learn this in 480, okay? I don't want to go too crazy on that. What's the transfer function? Let's do this on another page, 6. Okay. Let me just write this down quickly. Pole at 0.5, pole at 0.5, and then here is 0.5. I'm just gonna draw something quick. Okay. Well, this is not 0.5. This is J. Yeah, J.5, and then this is minus J.5. Okay. Everyone making sense of this? So if I were, well, I have a triple pole, right? H of Z. So I don't have anything on the bottom, but I do have things on the top. So if I wanted to, well, I have a pole right here. This is going to be
S minus 0.5.
Huh?
S minus 0.5.
It's going to be different because with poles in the Z domain, it's going to be
Z.
1 minus pole, right? And then Z to the minus 1, right? Pole 1. Is that correct with everybody? And then times 1, or times 1 minus P2Z1, right? Is that correct? And then, didn't make room. Times 1 minus P2 star Z minus 1. Does that make sense with everybody? Well, this one's going to be J. How would I want to introduce it? You let me know.
It's the same thing, right? 1 minus J.
You know what? I'm going to rewrite it. 1 minus 0.5. No, 1 minus, because this is plus. So that means if there's a pole right there, it's got to be plus 5Z minus 1. Is that correct with everybody? Right? Because if this Z to the minus 1 is equal to 0.5, right? So it's 0.5. No, it's got to be minus. Yeah, so, yeah, when I was an undergrad, I got confused too because it's Z minus 1, and the way you got to think about it, it's not, you have to look at this number, but not reciprocal, but if you wanted to, go ahead. What's his name? Yeah, it's whatever makes this disappear, okay? So if I have 0.5, right, if I'm at that point, that's 0.5, right? So if I put 0.5, because this is going to be under here, 0.5 over 0.5, that's going to be 1, right? But to get it to be 0, it's got to be minus. Everyone understanding what I'm trying to do? And then 1 minus, because I'm going to have a plus and a minus here. Yeah. I'm going to do this case right here, minus 0.5, I think it's J, yeah, J.5, Z minus 1, yeah, that's correct now. And then what am I going to have right here? 1 plus J.5, Z minus 1. Okay? Is that cool with everybody? But can anyone see my sin that I just did right now? If I were to multiply the top and the bottom by Z to the minus 1 3 times, like Z cubed, do You see that I'm missing 3 zeros in the middle? So what is this system truly? Ain't that cool? All right, so is that telling you something? Does a pole need to have a 0? Maybe. Z transforms are a little funny, but that's because it's digital. We're trying to visualize it on a computer. Okay, any questions about that? Yes?
You just add the J in terms of the y-axis.
Because it's real and imaginary. Okay, so everyone can do this. Okay, everyone follow what I'm trying to do here.
Yes.
Because I'm going to tell you this. Let me see. Where is it? What if I told you everything we did here, just flip it to Z? So everything we just did here, right? All this stuff, this problem right here. And this is the way I teach it, okay? What if this was all in Z? If you did this and this, can you do this in the Z transform? Everyone gonna get this right? Yes? What's up? Oh, you mean the block diagrams? Oh gosh, you see, this is so many. Please ask me good questions because there's a lot of equations. I don't want to go over things we've already learned. Okay. Anyways, 7. Okay, there's a lot of equations. Yes, there is going to be a block diagram. I have that down right here. See, yes, we do. Anyways, do I want to talk about that? Anyways, see, if he were to give you the following, I'm probably gonna cheat. Boom. Minus 1 over 4, and then z to the minus 1. I wonder if he draws it like this. Minus 1 over 2. Is that how I want to do it? No, because it goes down. This is, if it goes down like a waterfall, is it going up or is it going down? No, it's going up. Going up, okay? And then this is a gain of, I don't know, 1. Yeah. Y, X. He might give you something like this, and I think he might. Where you're trying to derive the actual transfer function from the block diagram, right? Does that make sense? Everyone remember the feedbacks and the feed forwards, right? Transpose direct form 1 was feed forward and then feed back, and then transpose direct form 2 was, well, was it backwards? Yeah, it was backwards. Feed back is first and feed forward is next. So that means, did I do this correctly? No, because we need this to feed back. I think I'm messing this one up in a way. I don't know if I want to show you that. Anyways, if he's gonna give you a block diagram, and he's gonna tell you, can you get the transfer function from that block diagram? Okay, can everyone do that? There's a whole bunch of problems, and I only have 13 minutes left. I don't want to talk too long, but yeah, point is, he's gonna give you a block diagram, find the transfer function, and then find the impulse response. Okay, everyone can do that. Impulse response, just the H of T's. Like this. Huh?
Like a closed loop one?
Oh yes, he may.
What do you say? I didn't hear his question.
Let's see. There's so many problems. I wish I didn't talk about things I didn't need to. X, Y, E, W, K, P or G. Was it P or G? I don't remember. This should be, this is, Good, thank you all. He's going to give you P and he's going to give you G. Solve for the transfer function. Can everyone do that? 370, E 370 intro? Not that hard. And then he's going to say, I'm just going to give it to you. Right? And then G. Right? Everyone can solve stuff like this, and then solve for when B is supposed to be stable. Everyone can do that. Any questions about that? Or I don't remember. He could flip these up two around because it's possible. Okay.
Do we just follow this step?
Yeah.
And then just like make sure it's on the cheat sheet?
Doesn't he only get you like 2 cheat sheets, or is it one?
He did one
One
full
those,
example of that too.
Okay. So you guys are confident with that? He went over that in class?
Yeah, it's on this.
Okay. Like literally, I'm going over notes, okay, and I'm trying to help you guys out, okay. I really want you guys to pass, okay.
Are there any other funky ones he's throwing?
Let's see the funky ones that I can tell you. It might be this one. The funky problem of the day is what's his name? H of n minus 1 or something like that, okay? Derive the transfer function. All right, not that hard. So basically, we're going to go from this to h of z, and then actually, no, not this one, sorry. H of z, this is going to be like not AE. It's going to be A P to the n, AP to the n, or a unit step or something like that, right? What's the z transform of the delta function? Easy. And then plus, what's the transfer function of this pole? Or you know what? I'm going to stop using A. I'm going to call it res for residue, right? Comp assignment 6. 1 over res over 1 minus p z minus 1. What are you going to do? You're going to do partial fraction expansion. Solve for, h of z, okay? And then you're going to combine, multiply this, multiply that, boom, all right? Solve for the heavy side or the hand flip or whatever you guys are calling it, okay? Just make it a nice equation. You can run this on MATLAB. Any questions about that? Cool. So yeah, that's the other funky one. Thank you. Let me see. And then he did give me some special funky ones that he wanted me to go over, but I don't think I'm gonna have time. Let's see. 355. Let me see. And I want people to take pictures of it. Be my guest. 355. 355. Let me see. 355. What? Where is it? Are we using the same book? 355. Okay, there we go. Can everyone see this one right here? H of s is equal to 2. I'm going to write it down. Homework. Because he gave me this problem. He's like, please give him this problem. I'm like, why? He's like, just do it. Shams. Okay. It's going to be 355. But in what do you call it? Solve for h of t, right? And then 3.25, and then 4.38. So for this guy right here, he says, solve for this guy right here, or 355. Answer to supplementary equations. Wait, hold up. 355. There it is. Shoes. Oh, God. Yeah, I'm going to make you guys take a picture of this. Go ahead. Yeah, I see this problem right here. Determine the overall system equation. Everyone can do that? He said he said this is a special problem. All right, what's the other problem? 325? I hope it's on the same page. Same side. No, it's going to be on the other. Oh, there it is. There it is. The output of a continuous time LTI system is found to be 2e to the 1 negative 3t ut. Find the impulse response. Find the output when the input is this little guy right there. I can't zoom into that. Let's see. Zoom in. Got to go deeper. Let's see. Better? Right? And then look. Who here doesn't have the Shams book? Everyone? Oh, you don't? You try to find it, please. Because guess what? The answer is right there. You see this A right here? It goes over all the solutions. Here's the solution. Take a picture. Cool. Taking the Laplace transform, you can see that. Right? Hence, I don't like doing this. I don't like being a point and teach professor. I don't like this. It's giving me, but we're running out of time, okay?
In the Shams book, it's chapter 3 and then chapter 4?
Yeah, chapter 3 and chapter 4. So yeah, if you just do all the problems from chapter 3 and chapter 4, which is what Dr. Stuber forces everyone to do, and somehow still fail. Actually, they fail because they don't even do it. Because he makes the homework like 2%.
Oh, yeah.
Yeah, that's great, right? But your final exam's like 40%, so give or take. Anyways, and then here's your final answer right there. See, I highly suggest getting a Shams book. It's really, really nice, and I'm still using it in my grad school years. It's great. It stumps even the CEOs that I talk to. They're engineers. They're like, "What the heck? This is great." It's like more like, think of it like brain pop, just the pop quiz of the day. Okay, what's the other question? 438. 438, because I think I want to end right here. 438. Man, there's a lot of good problems here.
Do you do these problems like Sudoku or like crossword?
If you wanted to treat this as your daily Sudoku, be my guest. It's pretty fun. I like it. Is this 438? Yeah, there he is. Ooh, that's another funny question for you guys. Unilateral Z transforms on the second order. Initial conditions. So I'm going to tell you this, and he's going to be a little unfair with you, but you better know this, please. It's a trivial. He's going to give you the initial condition when it's -1, -2, and -3, the delays, right? Okay? You guys know what to do, right? The first initial condition is going to be n equals -1, whatever that is. And then the second order is going to be n minus 2, and x of, or whatever, y of n is equal to -1 of whatever the initial condition, right? He's going to give you n at time -3, right? Don't use it. Okay? Someone's going to use it. He said someone did. And I'm like, why? Okay? Memorize the theory, but then know the theory, memorize this. You guys know what to do. You guys are engineers, okay? Are there any questions? Everyone see this right here? So, yeah, basically determine the output given this input and this initial condition, right? You see it says y -1, right? And then you see here, this is a second order equation. Why is it second order? Because it's got that second delay, right? The output is being delayed twice. That's why I made it second order. Cool? Everyone see how to do this? And then here's the answer.
He's going to give us an extra. Okay.
Yeah, so basically what I'm trying to say is he's going to give you y at -3 is equal to, I don't know, 1. Or actually not 1, -1. So then you don't know if it's going to be this one or this one, so he's going to know if you did it wrong. All right? But it's trivial, okay? You as the engineer, you got to know this, okay? But basically, if you don't come to class, you'll understand why. So if you come to class, you guys are doing great, okay? You'll be fine, okay? But other than that, are there any other final questions other than how to get this? I think Dr. Morris said you can get this book for free using like a student account. Did anyone do that? The free book? Pirate.
Does anybody have the pirate?
Please help it out, okay? Because honestly, what I'm trying to say is this exam isn't too tough, okay? Or it's tough, but basically if you practice engineering, you'll be okay. All right? Have a good day, everybody.